At the beginning of the 20th century, physics was almost complete. That, at least, was what many physicists believed. The laws of motion had been established by Newton, refined by Euler, Lagrange, and Hamilton. The laws of electricity and magnetism had been unified by Maxwell into 4 elegant equations that described every electromagnetic phenomenon ever observed. Thermodynamics had explained heat, entropy, and the behavior of gases. The atom had been confirmed as the fundamental unit of matter. There was a widespread sense that the remaining work of physics was to measure known quantities more precisely, not to discover fundamentally new laws. Then, in the span of about 30 years, from 1900 to 1930, the entire framework was replaced. Not corrected, not refined, replaced. The comfortable, deterministic, clockwork universe of classical physics, in which every particle has a definite position and velocity, in which the future is completely determined by the present, in which objects are always either here or there and not somewhere in between, turned out to be an approximation. An extremely good approximation for large objects moving slowly relative to the speed of light, but an approximation nonetheless. At the scale of atoms and electrons and photons, the scale of everything that matter is actually made of, a completely different set of rules operates. Rules that are so strange, so counterintuitive, so far from anything in ordinary human experience, that the physicists who discovered them spent years arguing about what they meant. Some of them never fully accepted the implications of their own equations. Richard Feynman, one of the greatest physicists of the 20th century, said, "I think I can safely say that nobody understands quantum mechanics." He did not mean nobody can use it or calculate with it. Quantum mechanics is the most precisely tested theory in the history of science, with predictions confirmed to more than 10 decimal places. He meant that nobody has an intuitive, gut-level understanding of what the theory is actually saying about the nature of reality. The theory works. What it means remains deeply contested. This video is an attempt to explain all of quantum physics, not just the famous strange parts, not just Schrödinger's cat and the uncertainty principle, but the actual theory, where it came from, what its fundamental principles are, how it describes the world, what it predicts, and why it is stranger than you probably think, even if you have been reading about it for years. We will go from the experimental crises of the late 19th century that forced quantum mechanics into existence, through the wave-particle duality and the uncertainty principle, through the Schrödinger equation and what it means, through quantum entanglement and superposition, to the measurement problem and the various interpretations that physicists have proposed to make sense of what the theory says about reality. This is not a shallow overview. It is a genuine attempt to explain quantum physics accurately and completely, at a level where you actually understand what the words mean, rather than just collecting a set of impressive-sounding phrases. Some of the concepts are genuinely hard. We will not pretend otherwise. But the difficulty is conceptual rather than mathematical. None of the mathematics required to understand what quantum mechanics is saying requires calculus or linear algebra. It requires only careful thinking and a willingness to let go of the intuitions that work perfectly well in everyday life, but that are simply wrong at the quantum scale. Let's start at the beginning. Chapter 1. The the crisis that started everything. Blackbody radiation and the ultraviolet catastrophe. Quantum mechanics did not emerge from a desire to build a new theory. It emerged from a specific experimental observation that classical physics could not explain. And the resolution of that one problem opened a door that led, ultimately, to a complete reconstruction of the foundations of physics. The problem was blackbody radiation. Every object that has any temperature above absolute zero emits electromagnetic radiation. The hotter an object is, the more radiation it emits, and the shorter the average wavelength of that radiation. A piece of iron at room temperature emits infrared radiation, heat, that is invisible to the naked eye. Heat it up and it begins to glow a dull red, then bright red, then orange, then yellow-white, then blue-white. The color of a hot object tells you its temperature. This is not an accident or a material property. It is a universal behavior called blackbody radiation, named for an idealized object that absorbs all radiation falling on it and re-emits radiation that depends only on its temperature, not on its composition. The experimental facts of blackbody radiation were well established by the late 19th century. The spectrum of radiation from a blackbody, the distribution of energy across different wavelengths, had a specific shape. It peaked at a wavelength that depended on temperature, shorter wavelengths, bluer light, at higher temperatures, dropped off steeply at very short wavelengths, and also dropped off at very long wavelengths. It had a hump shape. The problem was that classical physics could not reproduce this shape. According to classical physics, specifically, classical statistical mechanics applied to electromagnetic waves, the energy in a black body's radiation should increase without limit as the wavelength gets shorter. At very short wavelengths, the ultraviolet end of the spectrum and beyond, classical theory predicted infinite energy emission. This is called the ultraviolet catastrophe, and it was not a minor discrepancy. Classical theory was not slightly off. It predicted something physically absurd, something that was qualitatively different from what was actually observed. In 1900, Max Planck found a mathematical formula that perfectly matched the observed blackbody spectrum. He did not initially understand why it worked. He found it by trial and error, fitting the mathematics to the data. But when he worked backward to understand what assumptions would produce his formula, he found something disturbing. The formula required assuming that energy could not be exchanged in continuous amounts. Energy had to be exchanged in discrete chunks, in packets, whose size was proportional to the frequency of the radiation. The proportionality constant is now called Planck's constant and is denoted h. Its value is approximately 6.626 times 10 to the power of minus 34 joule seconds, an extraordinarily small number, which is why we do not notice quantization in everyday life. Planck called these packets quanta, singular quantum. The energy of each quantum is E equals hf, where f is the frequency of the radiation. High-frequency radiation, short wavelength, blue or ultraviolet light, comes in high-energy quanta. Low-frequency radiation, long wavelength, infrared or radio waves, comes in low-energy quanta. The reason the blackbody radiation spectrum falls off at short wavelengths is that high-frequency quanta have so much energy that they are statistically unlikely to be produced by thermal fluctuations at moderate temperatures. It is too expensive, energetically, to produce even a single quantum of very high-frequency radiation. Planck himself was uncomfortable with this conclusion. He viewed the quantization as a mathematical trick, a calculational device that happened to give the right answer, rather than a deep truth about nature. He spent years trying to derive his formula without assuming energy quantization. He could not do it. 5 years later, Albert Einstein took the quantization seriously and extended it dramatically. Chapter 2: Einstein's Photons, Light as Particles. In 1905, the same year he published Special, Relativity and his paper on Brownian motion, Einstein published a paper on the photoelectric effect that would eventually win him the Nobel Prize in Physics. Not relativity, not Brownian motion, the photoelectric effect. This paper is the one that, more than anything else, established that quantum mechanics was not just a mathematical trick, but a physical reality. The photoelectric effect is the observation that certain metals, when illuminated by light, emit electrons. This is useful. It is the basis of solar cells and photodetectors, but its detailed behavior was puzzling. Classical physics predicted that the energy of the emitted electrons should increase as the intensity of the light increases. It did not. The energy of the emitted electrons depended on the frequency of the light, not its intensity. Below a certain frequency, the threshold frequency, no electrons were emitted at all, regardless of how intense the light was. Above the threshold frequency, electrons were emitted immediately, even in extremely dim light, and the energy of each emitted electron depended only on the frequency of the light, not on how many photons were hitting the metal. This was completely inconsistent with classical wave optics. A wave's energy is distributed across its wavefront. A bright wave has more energy distributed over the same area, which should eventually provide enough energy to knock out an electron regardless of frequency. But that is not what happened. The electrons responded to frequency, not intensity. Einstein's explanation was radical. Light is not a continuous wave. It comes in discrete packets, quanta, each carrying energy E equals hf. These quanta are now called photons. Each photon interacts with a single electron. If the photon's energy is below the threshold needed to free an electron from the metal's surface, no electron is released, regardless of how many photons arrive, because no single photon has enough energy. If the photon's energy exceeds the threshold, the excess energy becomes the kinetic energy of the emitted electron. The energy of the emitted electron depends on the photon's energy, which depends on frequency, exactly what was observed. This was a profound claim. Classical physics had established, through centuries of experiment, that light is a wave. It diffracts, it interferes, it produces the characteristic patterns of wave behavior. Maxwell's equations, the crowning achievement of 19th century physics, described light as an electromagnetic wave. And now Einstein was saying that light is also in some sense a particle, that it comes in discrete bundles that behave in many ways like classical particles. Both were true. This is not a contradiction that can be resolved by choosing one or the other. Light genuinely behaves as a wave in some experimental contexts, diffraction, interference, and genuinely behaves as a particle in others, photoelectric effect, Compton scattering. This dual nature, wave-particle duality, is one of the foundational features of quantum mechanics, and it applies not just to light, but to everything. Electrons, protons, atoms, even molecules. Everything in the universe has this dual character. Chapter 3: The Bohr Atom and Discrete Energy Levels. In 1911, Ernest Rutherford's scattering experiments revealed that the atom has a nucleus, a tiny, dense, positively charged core surrounded by orbiting electrons. This was a spectacular discovery, but it immediately created a problem. According to classical electrodynamics, an orbiting electron is an accelerating charge. Circular motion is accelerating motion. An accelerating charge radiates electromagnetic energy. An electron orbiting the nucleus should therefore continuously radiate, losing energy, and spiral into the nucleus in a tiny fraction of a second. Classical physics predicted that atoms should not exist in stable form, but atoms do exist in stable form. The elements have characteristic properties. Matter is stable. In 1913, Danish physicist Niels Bohr proposed a solution. He simply postulated that electrons can only orbit the nucleus in certain specific orbits in which the electron's angular momentum is a whole number multiple of h over 2 pi, now called h bar or h bar. In these specific orbits, the electron does not radiate. It can jump between these allowed orbits by absorbing or emitting a photon, but only a photon with exactly the right energy to account for the difference between the two energy levels. Bohr's model was brilliant and successful. It explained the hydrogen spectrum, the specific wavelengths of light emitted by hydrogen gas, with extraordinary precision. The lines of the hydrogen spectrum correspond exactly to the energy differences between allowed orbits in Bohr's model. This was not a coincidence. The model was working. The hydrogen spectrum had been a puzzle for decades. Spectroscopists had catalogued the wavelengths of hydrogen's emission lines with great precision. The Balmer series in the visible, the Lyman series in the ultraviolet, the Paschen series in the infrared, but no theoretical explanation had existed for why hydrogen emitted those specific wavelengths and not others. Bohr's model explained every series in a single stroke. When an electron transitions from a higher energy orbit to a lower one, it emits a photon with energy equal to the difference between the orbit energies. Since the orbits have specific allowed energies, the photons have specific allowed energies, and therefore specific wavelengths. The Balmer series corresponds to transitions ending at the second energy level. The Lyman series corresponds to transitions ending at the first, ground energy level. The Paschen series corresponds to transitions ending at the third energy level. Every spectral series, every line, came out of the Bohr model with the right wavelength. But it was also completely ad hoc. Bohr had no explanation for why electrons only occupied certain orbits. He simply declared it by fiat. Why were some orbits allowed and others not? Why were angular momenta quantized in units of h-bar? What determined the allowed orbits for more complex atoms with multiple electrons? These questions remained unanswered for another decade, until Louis de Broglie proposed something extraordinary. Chapter 4, de Broglie's hypothesis, Matter as Waves. In 1924, in his doctoral thesis, Louis de Broglie proposed that if light, which was known to be a wave, could behave as a particle, then particles, which were known to be particles, might also behave as waves. He proposed that every particle has an associated wavelength, given by the de Broglie relation lambda equals h over p, where lambda is the wavelength, h is Planck's constant, and p is the particle's momentum. This was a brilliant insight that immediately explained Bohr's mysterious quantization condition. The reason electrons can only occupy certain orbits in the hydrogen atom is that only certain orbits allow the electron's de Broglie wavelength to fit as a standing wave, a wave that closes smoothly on itself as it completes the orbit with no destructive interference. The allowed orbits are precisely those in which an integer number of de Broglie wavelengths fit around the circumference of the orbit. All other orbits, the forbidden ones, are ones in which the electron wave would destructively interfere with itself. This was beautiful. It connected Bohr's mysterious rule to a physical picture. Electrons are waves, and atoms are like resonating cavities, supporting only the wavelengths that can form standing waves in the available space. But now there was a question. If electrons are waves, what is waving? What physical quantity oscillates as an electron propagates through space? Water waves are disturbances in the height of water. Sound waves are disturbances in air pressure. Electromagnetic waves are oscillations of electric and magnetic fields. What is the electron wave a disturbance of? This question took several more years and the work of several more physicists to answer. And the answer, when it came, was stranger than anyone had anticipated. Chapter 5. The Schrödinger equation. The wave function and what it means. In 1925 and 1926, the mathematical framework of quantum mechanics was developed independently by two physicists working in entirely different ways. Werner Heisenberg developed a formulation based on matrices, arrays of numbers, that represented observable quantities like position and momentum. Erwin Schrödinger developed a formulation based on wave equations. Both turned out to be mathematically equivalent, different representations of the same underlying theory. But Schrödinger's wave mechanics is the form most commonly taught and most intuitively accessible. The central object in Schrödinger's formulation is the wave function, denoted psi. The wave function is a mathematical function that describes the quantum state of a particle or system. It varies across space and time. It has a specific value at every point in space and at every moment in time. And the Schrödinger equation tells you how the wave function evolves over time. The Schrödinger equation itself is I h bar partial psi over partial t equals h bar psi, where I is the imaginary unit, the square root of -1, h bar is h bar, Planck's constant divided by 2pi. Psi is the wave function, partial derivative of psi, with respect to t is the rate of change of the wave function with respect to time, and h hat is the Hamiltonian operator, a mathematical object that encodes the total energy of the system. You do not need to understand the mathematics to understand what this equation is doing. It is saying, given the current state of the system, described by psi, here is how the state changes over time. It is a deterministic equation. Like Newton's second law, it completely specifies the future state of the system given its current state. If you know the wave function now, you can calculate the wave function at any future time. In this sense, the evolution of the wave function is perfectly deterministic. But here is the strangeness. The wave function is not directly observable. You cannot measure the wave function of an electron. What you can observe are the outcomes of experiments, positions, momenta, energies, spins, and the wave function's relationship to these observables is probabilistic. Max Born proposed the interpretation that is still accepted today. The squared magnitude of the wave function at any point in space, the absolute value of psi squared, gives the probability density of finding the particle at that point. The wave function itself is not the probability. It is the probability amplitude. The probability is the square of the wave function's magnitude. This is extraordinarily strange. The wave function is a complex valued mathematical object. It can have imaginary parts that is not directly observable. What is observable is the squared magnitude of this complex object, which gives probabilities. The particle does not have a definite position. It has a probability distribution of positions, specified by the wave function. When you measure the particle's position, you get a specific result, but this result is one possible outcome chosen according to the probability distribution, not a prediction of the only possible outcome, but a sample from a probability distribution. This is extraordinarily strange. The wave function is a complex valued mathematical object. It can have imaginary parts that is not directly observable. What is observable is the squared magnitude of this complex object, which gives probabilities. The particle does not have a definite position. It has a probability distribution of positions specified by the wave function. When you measure the particle's position, you get a specific result, but this result is one possible outcome chosen according to the probability distribution, not a prediction of the only possible outcome, but a sample from a probability distribution. This is not the same as classical ignorance. In classical physics, when we say we do not know the position of a particle, we mean the particle has a definite position and we just do not know what it is. The wave function is not our ignorance dressed up in mathematics. It is the complete description of the physical situation. There is no deeper layer of description, no hidden variables specifying the particle's actual position that the wave function is averaging over. The wave function is all there is. This was Bohr's insistence, and it forms the core of the Copenhagen interpretation. The particle does not have a position until it is measured. The question, where is the electron right now before I measure it, does not have an answer, because the electron is not anywhere in particular. It is described by a wave function that assigns probability densities to regions of space, and this is the complete physical description. Consider what this means for an electron in a hydrogen atom. The electron is not orbiting the nucleus like a tiny planet. It is described by a wave function that spreads throughout the atom. The wave function of the ground state of hydrogen is a spherically symmetric cloud of probability density, denser near the nucleus, falling off exponentially with distance. There is no trajectory, there is no orbit, there is only a probability distribution. If you measure the electron's position, you find it somewhere in this cloud, with probability proportional to the wave function's squared magnitude at that point. But between measurements, the electron simply is the wave function. It is the cloud, not a point particle moving through the cloud. Or at least, that is what the mathematics says. What it means for physical reality, whether the electron literally has no position before measurement, or whether there is some deeper description we are missing, is the measurement problem. which we will address in Chapter 11. Or at least that is the Copenhagen interpretation. We will return to the question of interpretations. Chapter 6, Superposition. The most counterintuitive fact in physics. Superposition is the principle that a quantum system can be in multiple states simultaneously, not in one state or another, with uncertainty about which, but genuinely, physically in multiple states at the same time. This is not a statement about our ignorance of the system's state. It is a statement about the system's actual physical situation. The classic demonstration of superposition is the double-slit experiment. Pass electrons, or photons, or atoms, the experiment works with any quantum particle, through a barrier with two narrow slits. On the other side, place a detector screen. Classical particles fired at the barrier would pass through one slit or the other, producing two bands on the detector screen. Waves passing through the barrier would diffract through both slits simultaneously and interfere with each other. The peaks and troughs of the waves from the two slits adding and subtracting, producing an interference pattern, a series of alternating bright and dark bands. What do quantum particles produce? An interference pattern, even when fired one at a time, even when fired so slowly that only one particle is in the apparatus at any moment, each particle producing a single point on the detector screen. The pattern of points that accumulates over many particles is an interference pattern. Not two bands, but many alternating bands. This means each individual particle passes through both slits simultaneously, not one slit or the other, both. If you close one slit, the interference pattern disappears and you get a single broad band, as expected from particles passing through a single opening. If you open both slits, each particle somehow knows both slits are open and behaves accordingly. The particle is in a superposition of went through the left slit and went through the right slit, both simultaneously, until it is detected at the screen. What happens if you put a detector at the slits to determine which slit each particle went through? The interference pattern disappears. The moment you obtain information about which path the particle took, it behaves like a particle that took a definite path, and you get two bands. This is not because the detector disturbs the particle physically. The effect occurs even when the which path information is obtained by methods that do not significantly disturb the particle's trajectory. What matters is whether the which path information exists in the world, not whether a conscious observer has looked at it. This is the measurement problem in miniature. Observing the system, obtaining information about it, changes its behavior. The superposition collapses into a definite state when measured. Why this happens, and what exactly constitutes a measurement, is the central unresolved question in the foundations of quantum mechanics. Let us make superposition more precise. In quantum mechanics, the state of a system is represented by a vector in an abstract mathematical space called Hilbert space. You do not need to understand the mathematics of Hilbert space to understand the physics. A basis of this space consists of the possible definite outcomes of a specific measurement. For example, if we measure whether the electron went through the left slit or the right slit, the basis states are left and right. A general quantum state is a linear combination, a superposition, of these basis states. psi equals alpha, left arrow, plus beta, right arrow. where alpha and beta are complex numbers, the probability amplitudes, whose squared magnitudes give the probabilities of each outcome. Alpha squared is the probability of finding the electron at the left slit. Beta squared is the probability of finding it at the right slit, and the absolute value of alpha squared plus the absolute value of beta squared equals 1. The probabilities must add up to 1. The key point: before measurement, the electron is not in state left or state right. It is in both simultaneously. The state is the full superposition. After measurement, the state collapses to whichever outcome was observed. The other term in the superposition disappears. This collapse is the mysterious part, a question that naturally arises. If superposition is a feature of all quantum systems, why don't we see cats in superpositions of alive and dead, or tables in superpositions of being in two places at once? The answer involves a process called decoherence. Large objects are made of enormous numbers of particles, each of which interacts with its environment, with air molecules, with photons, with other particles in the object. Each interaction entangles the object with its environment, which entangles the environment with the state of the object. In quantum mechanical terms, the object's superposition state becomes entangled with the environment in a way that makes the superposition effectively invisible to any local measurement. The superposition has not gone away. It has spread into the environment, becoming distributed across a vast number of particles in a way that is practically impossible to reverse or detect. This process, decoherence, happens extraordinarily quickly for macroscopic objects. For a grain of sand, the time scale for decoherence is something like 10 to the power of minus 23 seconds, far shorter than any measurement can probe. For an electron in carefully controlled laboratory conditions, decoherence can be slowed enough that quantum superpositions persist for milliseconds or even seconds. This is one of the central technical challenges in building quantum computers. Keeping the quantum bits, qubits, isolated from their environment long enough to perform computations before decoherence destroys the superposition. Decoherence explains why we do not observe macroscopic superpositions in everyday life, but it does not solve the measurement problem. It explains why the interference terms become practically unobservable, but it does not explain why measurement produces a single definite outcome, rather than a superposition of outcomes. That remains the hard problem. Chapter 7. Heisenberg's uncertainty principle, not what you think it is. The uncertainty principle is one of the most famous results in all of physics, and also one of the most frequently misunderstood. The common misunderstanding is that it says, there is a limit to how precisely we can measure position and momentum simultaneously, because measuring one disturbs the other. This is not quite what the uncertainty principle says, and the distinction matters. The correct statement: a quantum particle in a state of definite position has completely undefined momentum. A particle in a state of definite momentum has completely undefined position. More generally, any quantum state has an uncertainty in position, delta x, and an uncertainty in momentum, delta p, that satisfy. Delta x times delta. P greater than or equal to h bar over 2. The uncertainty is not a statement about measurement disturbance. It is a statement about what quantum states exist. There is no quantum state in which both position and momentum have definite values. such a state does not exist. The uncertainty is built into the structure of quantum mechanics. It is a consequence of the wave nature of particles and the mathematical relationship between position and momentum in quantum theory. To see why, consider the de Broglie relation. Lambda equals h over p. A particle with a definite momentum c has a definite wavelength lambda and is described by a wave that extends throughout all of space. A pure sine wave spread everywhere with no localization whatsoever. The position is completely undefined. To localize the particle, to confine the wave to a small region of space, you need to add waves of many different wavelengths. Adding waves of different wavelengths, different momenta, to create a localized wave packet means the particle has a range of momenta. The more localized the particle, smaller delta x, the wider the range of wavelengths needed, and therefore the wider the range of momenta, larger delta p. This is a mathematical fact about waves. It applies to sound waves, water waves, any wave. For quantum mechanical waves, because momentum and wavelength are related by the de Broglie relation, it translates into the Heisenberg uncertainty principle. The uncertainty principle has profound implications. It explains why atoms are stable. An electron confined to the tiny volume of an atomic nucleus would have such a small delta x that its delta p would be enormous, giving it an energy that is more than enough to escape the nucleus. The minimum size of an atom is determined by the balance between the attractive force of the nucleus and the quantum mechanical uncertainty that prevents the electron from being confined too tightly. Atoms have the sizes they have because of the uncertainty principle. It also implies that the vacuum, empty space, is not truly empty. The uncertainty principle applies to fields as well as particles. Even in a region of space with no particles, the field values have quantum uncertainty. They cannot be both 0 and 0 simultaneously, analogous to having both 0 position and 0 momentum. The vacuum, therefore, has irreducible quantum fluctuations, and these fluctuations have measurable physical consequences. This is not speculation. The Casimir effect, an attractive force between closely spaced metal plates in vacuum, caused by vacuum fluctuations, has been measured to high precision. There are other pairs of quantities besides position and momentum that satisfy similar uncertainty relations. Energy and time satisfy delta E times delta T greater than or equal to h bar over 2. This means a quantum state that exists for only a short time, small delta T, must have a spread of energies, large delta E. This is why excited states of atoms that decay quickly have broad spectral lines. The short lifetime means large energy uncertainty, which means the emitted photon has a range of energies, which means the spectral line is broad rather than sharp. Pairs of quantities that satisfy uncertainty relations are called complementary or conjugate. Position and momentum are conjugate. Energy and time are conjugate. They represent different perspectives on the same underlying physical reality, and you cannot have complete information about both simultaneously. This is not a limitation of measurement technology. It is a fundamental feature of what physical states are. Chapter 8. Quantum spin, the property that has no classical analog. Every electron, proton, neutron, and photon has a property called spin. This is not a metaphor. It is a real physical property of particles with measurable effects. But it is not what it sounds like. Electrons do not actually spin in the classical sense of a ball rotating about an axis. Spin is a quantum mechanical property with no classical analog. It behaves, mathematically, like angular momentum. It adds like angular momentum. It interacts with magnetic fields like angular momentum. But it is not caused by physical rotation. It is an intrinsic property of particles, as fundamental and inalienable as their mass or electric charge. The spin of an electron is characterized by a quantum number s equals 1/2. What this means is that when you measure the component of the electron's spin along any axis, you always get one of exactly two possible values: plus h bar over 2 or minus h bar over 2. These two values are commonly called spin up and spin down, and are written as vertical, bar up arrow, vertical bar, and vertical bar, down arrow, vertical bar. No measurement of spin along any axis ever gives any other value. It is always one of these two. Before measurement, a general electron spin state is a superposition. Vertical bar, psi, vertical bar equals alpha vertical bar, up arrow vertical bar, plus beta vertical bar, down arrow vertical bar. The probability of measuring spin up is vertical bar alpha vertical bar squared. The probability of measuring spin down is absolute value of beta squared. This is the same structure we saw with the double slit experiment. Now here is something subtle and important. Suppose you measure the electron's spin along the z-axis and get spin up. The electron is now in state vertical bar, up arrow vertical bar, along the z-axis. If you immediately measure again along the z-axis, you get spin up again with certainty. The state has not changed. But if instead you measure along the x-axis, you get spin up or spin down along x with equal probability. And after this measurement, the electron is now in a definite state along the x-axis, but its z-spin has become indefinite again. The spin measurements along different axes are complementary in exactly the same way that position and momentum are complementary. Measuring spin along the z-axis makes the x-spin indefinite. Measuring spin along the x-axis makes the z-spin indefinite. There is a spin uncertainty principle analogous to the position momentum uncertainty principle. Spin is important for two major reasons. First, it determines whether a particle is a fermion or a boson, a distinction with profound consequences for the collective behavior of many particle systems. Particles with half-integer spin, 1/2, 3/2, 5/2, are fermions. They obey the Pauli exclusion principle and cannot be in the same quantum state. Electrons, protons, and neutrons are all fermions with spin 1/2. The Pauli exclusion principle is why atoms have the structure they do, why the periodic table has the pattern it has, why metals are solid and have their specific electrical properties, why neutron stars don't collapse further. Particles with integer spin, 0, 1, 2, are bosons. They can be in the same quantum state and actually prefer to. Photons are bosons with spin 1. This is why a laser, in which many photons occupy exactly the same quantum state, is possible. Bose-Einstein condensates, in which many atoms occupy the same ground state at very low temperatures, are another example. Second, spin interacts with magnetic fields. The electron's spin creates a magnetic moment. The electron behaves like a tiny bar magnet, whose orientation in space is determined by its spin state. When placed in a magnetic field, the energy of the electron depends on the orientation of its spin relative to the field. Spin up along the field is lower energy. Spin down is higher energy. This splitting of energy levels by a magnetic field, the Zeeman effect, allows the measurement of spin through the observation of spectral lines. The related phenomenon of nuclear magnetic resonance, in which nuclear spins in a magnetic field absorb and emit radio waves at specific frequencies, is the basis of MRI, magnetic resonance imaging. Chapter 9: The Pauli exclusion principle. Why matter is solid. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. An electron in an atom is characterized by 4 quantum numbers. The principal quantum number, n, describing the energy level, the angular momentum quantum number, L, the magnetic quantum number, m, and the spin quantum number, which can be +1/2 or -1/2. The Pauli exclusion principle says no two electrons in the same atom can have all 4 quantum numbers the same. This single principle explains more about the physical world than almost any other rule in physics. It explains the structure of atoms. In hydrogen, the single electron occupies the lowest available energy state, the ground state. In helium, 2 electrons can occupy the same energy level because they can have opposite spins. In lithium, the 3rd electron cannot go into the first energy level. Both spin states of the first level are full and must go into the 2nd energy level. In beryllium, the 4th electron fills the 2nd available state in the 2nd energy level, and so on, filling up the available states in order of increasing energy, with the Pauli principle preventing more than 2 electrons per energy level, 1 spin up, 1 spin down, building up the shell structure of the periodic table. The periodic table, the organization of elements by atomic number with the repetition of chemical properties at regular intervals, is directly a consequence of the Pauli exclusion principle and the quantum mechanical structure of atomic energy levels. The noble gases, helium, neon, argon, krypton, xenon, are chemically inert because they have completely filled shells. Adding or removing electrons would require going to a much higher energy level. The alkali metals, lithium, sodium, potassium, are highly reactive because they have a single electron in an otherwise empty outer shell, which can easily be removed or shared. The halogens, fluorine, chlorine, bromine, are reactive because they are 1 electron short of a filled outer shell, which they will strongly attract. The Pauli exclusion principle also explains why matter is solid, why you cannot walk through walls. If electrons were bosons, if they could all occupy the same quantum state, all the electrons in a solid would collapse into the same lowest energy state, and matter would not have the rigid, space-occupying structure it does. It is the Pauli exclusion principle that forces electrons into successively higher energy states and gives atoms their finite size, which in turn gives matter its volume and resistance to compression. In extreme contexts, the cores of white dwarf stars, for instance, the Pauli exclusion principle is literally preventing gravitational collapse. A white dwarf is held up against its own gravity not by thermal pressure, the star is no longer burning nuclear fuel, but by electron degeneracy pressure. The pressure that arises because the Pauli principle forbids all the electrons from being compressed into the same quantum state. If you compress the white dwarf, the electrons are forced into higher and higher energy states. Because the lower states are already occupied, and this increasing energy resists the compression. A white dwarf with a mass less than the Chandrasekhar limit, approximately 1.4 solar masses, is stable against gravitational collapse because of this quantum mechanical pressure, despite having no ongoing energy source. Chapter 10: Quantum Entanglement. The spookiest part. Quantum entanglement is the phenomenon in which two or more particles are correlated in their quantum states in a way that cannot be explained by any classical mechanism, including any mechanism in which each particle carries hidden information about how it will respond to measurements. To understand entanglement, start with two electrons. Prepare them so that their total spin is 0. One spin up, one spin down. But the spins are indeterminate. The state is a superposition of electron 1 up, electron 2 down, and electron 1 down, electron 2 up. In quantum notation, vertical bar, psi vertical bar equals open parenthesis 1 over the square root of 2 close parenthesis, open parenthesis, vertical bar, up arrow, 1 vertical bar, down arrow, 2 minus vertical bar, down arrow, 1 vertical bar, up arrow, 2 close parenthesis. Now separate the two electrons by any distance, a meter, a kilometer, a light year. The two electrons are still in this entangled state. Measure the spin of electron 1 along the z-axis. You get either spin up or spin down with equal probability. Suppose you get spin up. Immediately, faster than any signal could travel between them, the state of electron 2 is determined. It is spin down. If you had measured spin down for electron 1, electron 2 would be spin up. The measurement outcome of one electron instantly determines the outcome of the other, regardless of the distance between them. Einstein, Podolsky, and Rosen noticed this feature of quantum mechanics in 1935 and proposed it as evidence that quantum mechanics was incomplete. Their argument, the EPR paradox, was that either there is spooky action at a distance, an instantaneous influence of one particle on the other, which seemed to violate relativity, or the particles have definite spin states all along, carried as hidden local variables, and quantum mechanics is simply incomplete, failing to describe these hidden variables. In 1964, physicist John Bell proved a theorem that made this choice empirically testable. Bell showed that any theory in which particles carry hidden local variables, any theory that reproduces the quantum correlations without spooky action at a distance, must satisfy specific mathematical inequalities, Bell inequalities. But quantum mechanics predicts correlations that violate these inequalities. Starting in the 1970s and reaching their most definitive forms in the 2000s and 2020s, experiments have conclusively demonstrated that Bell's inequalities are violated, exactly as quantum mechanics predicts. The most rigorous tests, the loophole-free Bell tests of 2015, performed by Henson and colleagues at Delft University and by other groups, have closed all known experimental loopholes and established, beyond any reasonable doubt, that the correlations between entangled particles cannot be explained by any local hidden variable theory. What does this mean? It means nature is non-local in a specific sense. The correlations between entangled particles are stronger than any local classical mechanism can produce. The two particles are connected in a way that transcends spatial separation. But, and this is crucial, This non-locality cannot be used to send information faster than light. The outcomes of individual measurements on entangled particles are random. You cannot control what outcome you get when you measure your particle. The correlation only becomes apparent when the results of measurements on both particles are compared, which requires classical communication limited to light speed. Entanglement is a form of non-locality that cannot be exploited for faster-than-light communication. Entanglement is not just a curiosity, it is the resource that makes quantum information processing possible. Quantum computers exploit entanglement to perform certain computations that are exponentially faster than any classical computer. Quantum cryptography uses entanglement to enable communication protocols that are provably secure against any eavesdropping. Quantum teleportation, the transfer of a quantum state from one particle to another at a distant location, uses entanglement as the resource, though it still requires classical communication and does not allow faster-than-light information transfer. The specific correlations produced by entangled particles have no classical explanation. They are a genuine signature of the quantum mechanical structure of reality, evidence that the universe is, at its foundations, non-separable in a way that classical physics never anticipated. One clarification on what entanglement does and does not mean is essential. It does not mean that measuring one particle causes something to happen to the other particle in the sense of sending a signal. The outcomes of measurements on entangled particles are random. You cannot choose what result you get. If you measure your electron's spin and get up, you instantly know that the distant electron is down. But you cannot use this to send a message. You cannot choose to get spin up. It is random. The distant observer's sequence of results is also random, and they cannot tell from their own results alone whether their particle is entangled with yours or not. The correlation only becomes evident when both sets of results are compared, which requires classical communication at ordinary speeds. This is the no-communication theorem of quantum mechanics. Entanglement cannot be used to transmit information faster than light. Einstein's special relativity is safe. Entanglement is non-local in its correlations, but not in its ability to transmit information. What entanglement does reveal is something subtle and profound. The universe cannot be decomposed into independent parts in the way that classical physics assumed. Two entangled particles, regardless of their separation, are described by a single quantum state that cannot be written as a product of two independent states. They are not two separate systems. They are one system that happens to be spatially distributed. The quantum state of the whole is not determined by the quantum states of the parts. This holism, the irreducibility of the whole to its parts, is one of the most fundamental differences between quantum mechanics and classical physics, and it has deep implications for how we understand composite systems, including molecules, materials, and ultimately the universe as a whole. Chapter 11, The Measurement Problem. What happens? When you look of all the conceptual difficulties in quantum mechanics, the measurement problem is the deepest. It is not a problem that has been solved and then simplified for popular presentation. It is an active area of research and philosophical debate among professional physicists and philosophers of physics. It sits at the intersection of the most precise physical theory ever developed and the most ancient philosophical questions about the nature of reality and observation. The measurement problem arises directly from the mathematics of quantum mechanics, and stating it precisely requires 3 ingredients. The first ingredient: according to the Schrödinger equation, quantum systems evolve deterministically. The wave function evolves smoothly and continuously, according to a perfectly well-defined rule. If you know the wave function now, you can calculate the wave function at any future time. There is no randomness in the Schrödinger equation. The second ingredient: according to the Born rule, when you measure a quantum system, you get a specific, definite outcome, one of the possible values of the measured quantity, with probability given by the squared magnitude of the wave function at that outcome. This is where randomness appears. The specific outcome you get is not determined by the wave function. It is a random draw from the probability distribution the wave function specifies. The third ingredient: after measurement, the wave function changes discontinuously. If the electron was in a superposition of position states, after you measure its position and find it at a specific location, its wave function is suddenly concentrated at that location. The other components of the superposition have disappeared. This is the collapse of the wave function. It is not described by the Schrödinger equation. It is a separate rule, sometimes called the projection postulate or the collapse postulate. Added alongside the Schrödinger equation. The problem: these 3 ingredients are inconsistent. The Schrödinger equation is linear. If the electron is in a superposition of states, then the measuring apparatus, which is a physical system governed by quantum mechanics, should also end up in a superposition of states reflecting the different measurement outcomes. If the electron is in a superposition of here and there, and the measuring apparatus is designed to point left if the electron is here, and right if the electron is there, then after the measurement, the apparatus should be in a superposition of pointing left and pointing right. But we never see a measuring apparatus in a superposition. We always see a definite outcome. More precisely, if we apply the Schrödinger equation to the combined system of electron plus measuring apparatus, we do not get collapse. We get a superposition of the whole system, electron plus apparatus, in which the electron and apparatus are entangled. To get collapse, we need to apply a different rule, the projection postulate, at some point. But the theory does not tell us when to apply this rule, or what counts as a measurement, or what makes the apparatus special compared to any other physical system. John von Neumann showed in 1932 that you can push the collapse back arbitrarily far without resolving it. If the apparatus is in a superposition, add another apparatus to measure the first. Now the second apparatus is in a superposition. Add a third, and eventually add a conscious observer. Von Neumann argued that the chain of physical systems can be extended indefinitely, and the collapse can only be stopped at the point where a conscious observer becomes aware of the result. This is the role of consciousness in quantum mechanics that some physicists and philosophers have taken seriously. The idea that consciousness causes collapse. Most physicists find this unsatisfying, but no better solution was agreed upon for decades. The measurement problem is sometimes dismissed as a philosophical issue rather than a physics issue. The suggestion being that since quantum mechanics makes correct predictions, the measurement problem is just a matter of interpretation not a problem that affects the calculations. This dismissal is incorrect. The measurement problem asks a question that is physically meaningful. What is the physical process by which definite outcomes arise from quantum superpositions? This question matters for understanding the relationship between quantum mechanics and classical mechanics, for designing quantum computers, which must understand when decoherence destroys quantum superpositions, and for any future theory that extends quantum mechanics. It is not merely a semantic puzzle. There is also a practical sharpening of the problem. Decoherence, discussed briefly in Chapter 6, partially addresses the measurement problem by explaining why we do not observe macroscopic superpositions. When a quantum system interacts with a large environment, the system's superposition becomes entangled with the environment in a way that makes the interference between branches unobservable to any local measurement. The different branches of the superposition decohere from each other. They stop interfering. But decoherence does not eliminate the superposition. It just makes the interference invisible. The wave function still contains all the branches. The apparatus is still, technically, in a superposition, but the branches can no longer interfere with each other. Decoherence explains the appearance of classical outcomes without actually producing them. The full superposition persists at the level of the total wave function. It is only effectively classical from the perspective of local subsystems. Wojciech Zurek's contribution to decoherence theory in the 1980s and 1990s sharpened our understanding significantly beyond the basic decoherence picture. Zurek developed the concept of einselection, environmentally induced superselection, which explains not just why superpositions become practically unobservable, but why specific states emerge as the classical states that are robustly preserved through environmental interaction. The key insight is that not all superpositions decohere equally. When a quantum system interacts with its environment, some states, called pointer states, are particularly robust. They can interact with the environment repeatedly without losing their identity. A superposition of two pointer states decoheres rapidly. A pointer state itself is relatively stable. For a measuring apparatus, the pointer states are the states in which the pointer is in a definite position, pointing left or pointing right. These are the states that are robust to further environmental interactions, because a macroscopic pointer pointing left interacts with the environment in a very different way from one pointing right, and the environment rapidly becomes correlated with the pointer's position. This correlation is what makes the measurement outcome classical. Once the pointer's position is correlated with many environmental degrees of freedom, it is effectively classical from any local perspective. It cannot be reversed, and the different outcomes cannot interfere. This is more than just an explanation of why we see definite outcomes. It explains why the outcomes we see are in terms of position states rather than, say, energy states or momentum states. The preferred classical variables, the ones that survive decoherence, are those that commute best with the system-environment interaction Hamiltonian. For most macroscopic objects interacting with air molecules and photons, position commutes well with these interactions. This is why the classical world is formulated in terms of positions rather than superpositions of positions. Zurek's framework, called quantum Darwinism, extends this further. The reason we all agree on the same classical world is that the environment becomes correlated with a system's state in a specific way, and multiple independent observers can extract the same information from independent fragments of the environment. The environment acts as a communication channel, redundantly encoding classical information about macroscopic objects and allowing many observers to reach the same conclusions without directly interacting with the system. This redundant encoding is what makes the classical world objective. The same object is measured by different observers, and they agree because they are all reading the same environmental record. This is the point at which interpretations of quantum mechanics diverge. Chapter 12. Interpretations of quantum mechanics. Many worlds, Copenhagen and beyond. There are at least 8 distinct interpretations of quantum mechanics that have been seriously developed and defended in the physics and philosophy literature. They all make the same experimental predictions. They cannot be distinguished by any experiment currently conceivable. But they disagree fundamentally about what quantum mechanics is saying about the nature of reality. This is an unusual situation in physics, and it is worth taking seriously. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, is the oldest and historically the most widely taught. It can be summarized roughly as follows. Quantum mechanics gives correct predictions for the outcomes of measurements. The wave function is a mathematical tool for computing probabilities. It is not a direct description of physical reality. Physical quantities do not have definite values before measurement. The question, what is the electron doing between measurements, is meaningless. It cannot be answered by any observation, and therefore it is not a legitimate scientific question. The wave function collapses when a measurement is made, and the collapse is a fundamental, irreducible aspect of quantum mechanics rather than something to be derived from deeper principles. The Copenhagen interpretation has the advantage of internal consistency. It avoids the measurement problem by declaring that the question it poses is illegitimate. But it has the disadvantage of invoking the concept of measurement without defining it precisely, and of being vague about where the quantum classical boundary is. The quantum world in Copenhagen somehow gives way to the classical world at the level of measurement. But where exactly this transition happens and what physical process accomplishes it is never specified. This vagueness bothered many physicists deeply, including Einstein, who never accepted Copenhagen. The many worlds interpretation proposed by Hugh Everett III in 1957 in his doctoral thesis at Princeton takes the Schrödinger equation completely seriously and removes the collapse postulate. In the many worlds interpretation, there is no collapse. The wave function always evolves according to the Schrödinger equation. When a measurement is made and the apparatus becomes entangled with the quantum system, the combined system, apparatus plus quantum particle, enters a superposition of states. All the branches of this superposition are equally real, the universe branches. In one branch, the apparatus read spin up. In another branch, the apparatus read spin down. Both branches exist. Neither collapses. The many worlds are not exotic additional universes invented to solve the problem. They are simply the branches of the wave function, which was always there in the mathematics. What Everett noticed is that if you take the mathematics seriously and remove the additional collapse postulate, the theory is automatically many-branching, and the appearance of definite outcomes in each branch can be derived from the structure of the wave function and decoherence. The many worlds interpretation is currently the most popular interpretation among physicists who have thought carefully about the foundations of quantum mechanics. According to several surveys of physicists specializing in quantum foundations, it has the significant advantage of being a complete, determinate, and consistent physical theory. It describes exactly what is happening without adding an unexplained collapse or invoking undefined concepts like measurement or observer. Its significant disadvantage is that it requires the existence of an enormous, essentially infinite, number of parallel branches of reality, most of which you have no access to and no evidence for, beyond the internal evidence of the theory's consistency. Many physicists find this ontologically extravagant. There is also an ongoing technical debate about how to derive the Born rule, the probability rule, from the many worlds framework, whether the specific quantum probabilities can be justified from the theory's structure or must be added as a separate postulate, even in the Everett picture. The pilot wave interpretation, also called de Broglie-Bohm theory or Bohmian mechanics, developed by David Bohm in 1952, takes a completely different approach. In Bohmian mechanics, particles have definite positions at all times. There are no superpositions in the sense of being in many places at once. Instead, particles move under the influence of both classical forces and a quantum potential derived from the wave function. The wave function guides the particle. It is a real physical field that acts on the particle, not merely a probability calculator. The wave function still satisfies the Schrödinger equation, but the particle always has a definite position and a definite trajectory. In Bohmian mechanics, the apparent randomness of quantum mechanics arises from our ignorance of the particle's initial position, which is distributed according to the Born rule probability distribution. Once the initial conditions are fixed, the particle's trajectory is completely determined. There is no collapse. The wave function always evolves smoothly, and collapse is an effective description of what happens to the wave function relative to the particle's actual position. There is no measurement problem. Measurements have definite outcomes because particles have definite positions, and the measurement apparatus's pointer has a definite position. The cost. Bohmian mechanics is explicitly non-local. The quantum potential depends on the positions of all particles simultaneously, so the motion of any particle can depend instantaneously on the positions of all other particles, regardless of separation. This non-locality is consistent with the Bell inequality violations we discussed in Chapter 10, and it is non-signaling. It cannot be used to send information faster than light, but it is deeply at odds with the spirit of relativity. Extending Bohmian mechanics to be consistent with quantum field theory, the relativistic extension of quantum mechanics, is technically challenging and not fully accomplished, which limits its appeal to physicists who work on high-energy physics. Bohmian mechanics has one historical significance that extends beyond its role as an interpretation. David Bohm proved in 1952 that a hidden variable theory could reproduce all the predictions of quantum mechanics. at least for non-relativistic quantum mechanics. This directly contradicted a theorem that von Neumann had published in 1932, which had been widely interpreted as proving that no hidden variable theory could reproduce the predictions of quantum mechanics. For 20 years, von Neumann's theorem had been taken as a proof that quantum mechanics was irreducibly probabilistic, that the randomness was fundamental, not a reflection of our ignorance of hidden variables. Bohm's theory showed that von Neumann's theorem had a loophole. John Bell identified the loophole in 1966. Von Neumann's theorem assumed that hidden variable observables must obey the same additivity rules as quantum mechanical observables, an assumption that Bohmian mechanics violates. Once this assumption was identified as the crucial one, the proof of impossibility was revealed to be a proof that a specific type of hidden variable theory was impossible, not that all hidden variable theories were impossible. The existence of Bohmian mechanics as a working example proved this directly. This episode has lessons for physics beyond the specific case of quantum foundations. It illustrates that mathematical proofs in physics can be overturned not by finding mathematical errors, but by identifying hidden assumptions that the proof depends on. The physical content of a theorem is only as strong as the physical justification for its assumptions. Von Neumann's theorem was mathematically correct, but physically misleading, because the assumption it required was not physically necessary. The history of quantum foundations is full of similar episodes, proofs of impossibility that turned out to be proofs of impossibility given specific assumptions, not absolute proofs. The relational interpretation, developed by Carlo Rovelli in 1996, proposes that quantum states are not absolute properties of systems, but are always relational. They describe the state of one system relative to another. There is no absolute wave function of the universe. The value of an observable is only defined relative to a specific interaction between two systems. This interpretation resolves the measurement problem by dissolving it. There is no measurement problem because there is no absolute, observer-independent physical state to describe. The collapse is not a physical process. It is simply the update in the description of the system relative to the measuring apparatus. The cubism, quantum Bayesianism interpretation, developed by Christopher Fuchs, Rüdiger Schack, and colleagues, goes further in the same direction. In cubism, quantum mechanics is not a description of the world at all. It is a normative theory for how an agent should update their beliefs, in the formal, probabilistic sense, in the light of experience. The wave function is not a physical object. It is an agent's catalog of beliefs about future experiences. The Born rule is a consistency requirement on an agent's beliefs, analogous to the rules of probability theory. There is no measurement problem because the wave function is not a physical thing that could be in a superposition. It is just a belief state, and beliefs do not collapse. The advantage of cubism is that it is completely free of the measurement problem and of the non-locality worries that afflict other interpretations. The disadvantage is that it makes quantum mechanics explicitly about agents and experiences, which many physicists find uncomfortably subjective. If quantum mechanics is a theory about what agents should believe rather than about what the world is like, then it seems to give up on the goal of providing an objective description of physical reality. none of these interpretations is universally accepted. The debate continues among physicists and philosophers of physics, and the choice of interpretation ultimately reflects a balance between different desiderata. Ontological parsimony. How many things does the theory posit? Explanatory completeness. Does the theory actually explain what it needs to explain? Mathematical elegance and compatibility with other well-established physical theories. What is not in dispute is the formalism of quantum mechanics itself. All interpretations agree on the mathematics and therefore on all the predictions. Chapter 13. Quantum Field Theory. The deeper layer. Non-relativistic quantum mechanics. The theory developed by Schrödinger, Heisenberg, Dirac, and Born in the 1920s is extraordinarily successful at describing atoms, molecules, and the behavior of matter at room temperature. But it is incomplete. It does not incorporate special relativity. It treats particles as if they can be localized and tracked, which becomes problematic when energies are high enough to create new particles from energy via E equals mc squared. And it treats forces as if they are instantaneous, failing to account for the finite speed of signal propagation that relativity requires. The solution is quantum field theory, QFT, which combines quantum mechanics with special relativity into a framework that treats particles not as fundamental objects, but as excitations, quantum jumps of underlying quantum fields that permeate all of space. In quantum field theory, the electron is not a particle in the classical sense. It is a quantum of the electron field, a field that exists everywhere in space, in every direction, all the time. The field has a ground state, the vacuum, in which no electrons are present. An electron is a specific excitation of this field, a localized, quantized vibration of the field that behaves like a particle. When an electron is created, for example, in a pair production event where a photon creates an electron and a positron, it is the field being excited. When an electron is annihilated, the field returns toward its ground state. The same applies to every other particle. The photon is a quantum of the electromagnetic field. The quarks are quanta of the quark fields. Every type of particle corresponds to a quantum field. The universe is not made of particles. It is made of fields. And the particles we observe are the quantized excitations of those fields. This change in perspective resolves several conceptual problems with non-relativistic quantum mechanics and introduces extraordinary new features. The first new feature is the possibility of particle creation and annihilation. In non-relativistic quantum mechanics, particle number is fixed. You start with n particles and always have n particles. In quantum field theory, energy can be converted to particles and back. A photon with sufficient energy can create an electron-positron pair. An electron and positron can annihilate to produce two photons. The number of particles of each type is not conserved. What is conserved are charges, like electric charge, baryon number, lepton number, rather than particle numbers. The second new feature is the vacuum. In quantum field theory, the vacuum is not empty. Every quantum field in its ground state has vacuum fluctuations, a consequence of the uncertainty principle applied to fields rather than particles. These fluctuations are real and have measurable physical consequences. The Casimir effect, mentioned earlier, is one example. The Lamb shift, a tiny but measurable correction to the energy levels of hydrogen, first measured in 1947 by Willis Lamb, is another. The electron in hydrogen interacts with the vacuum fluctuations of the electromagnetic field, which shifts its energy levels by a small but precisely calculable and measurable amount. The vacuum fluctuations of quantum fields are also responsible for the phenomenon of virtual particles, a concept that is widely misunderstood in popular science. Virtual particles are not actual, particles fleetingly popping into and out of existence. They are mathematical terms in the perturbative expansion of quantum field theory calculations. Feynman diagram contributions that represent intermediate states in a process. When an electron and a positron annihilate, the process can proceed through many different intermediate states, some of which look like they involve particles that do not satisfy the standard energy-momentum relation. They are off-shell. These are the virtual particles. They are calculation tools, not observable physical entities. The result of summing all these virtual contributions is a correct prediction for the observable process. Treating virtual particles as actual particles that momentarily appear and disappear, carrying energy away in violation of conservation laws, is a common misconception that quantum field theory does not support. The third new feature is the precise treatment of interactions. In classical physics, forces are described by fields. The electromagnetic force is described by the electromagnetic field, and charged particles interact by exchanging energy with this field. In quantum field theory, the force carriers are also quantized. The electromagnetic force between two electrons is transmitted by the exchange of photons. Virtual photons, in the Feynman diagram sense. The detailed calculation of this exchange gives the quantum corrections to the classical Coulomb force, producing predictions that have been tested to extraordinary precision. The process by which quantum field theory calculations are made to give finite answers, rather than the infinite answers that naively appear, is called renormalization, and it is one of the most technically impressive and philosophically contested procedures in all of physics. When you calculate, in quantum electrodynamics, the probability that two electrons scatter off each other, you must sum contributions from an infinite number of Feynman diagrams with more and more internal loops representing virtual particle processes. Each diagram with an additional loop contributes a smaller amount to the total, but the individual loop integrals diverge. They are infinite. The integral over all possible momenta of the virtual particles in each loop does not converge. The solution, renormalization, involves a procedure that initially sounds like a cheat. The theory is formulated with bare parameters, a bare mass for the electron and a bare charge, that are formally infinite. The physical observed mass and charge of the electron are the bare values plus the infinite quantum corrections, which combine to give the finite observed values. By defining the theory in terms of the physical parameters rather than the bare parameters, all the infinities cancel out, and the remaining predictions are finite and calculable. The procedure works to arbitrary precision. It can be extended to any order of perturbation theory and always gives a finite answer. Richard Feynman, who received the Nobel Prize for his contributions to quantum electrodynamics, including the invention of Feynman diagrams, described renormalization as a dippy process and hocus pocus in his Nobel lecture. He was not being falsely modest. The infinite bare parameters that are added and subtracted have no physical interpretation. The justification for the procedure is entirely pragmatic. It gives correct answers. Whether it has a satisfying conceptual foundation, whether the infinities reflect some deeper physical reality, or are artifacts of an approximation scheme that breaks down at very short distances, remains a subject of debate. The more modern view, associated with Kenneth Wilson's work in the 1970s on the renormalization group, provides a more satisfying conceptual framework. The infinities in quantum field theory arise because we sum over all possible momenta of virtual particles, including arbitrarily high momenta. But very high momenta correspond to very short distances. Distances far shorter than anything we have tested experimentally. Wilson's insight is that a quantum field theory can be understood as an effective field theory, a description that is valid below some energy scale and that may break down at higher energies where new physics, like quantum gravity, takes over. When understood this way, the renormalization procedure is not a cheat, but a systematic way of incorporating the effects of high-energy physics that we do not yet know into a small number of parameters, like the electron mass and charge, that we measure experimentally. The renormalizable theories, like QED, are precisely those whose predictions at accessible energies are independent of the unknown high-energy physics. The most precisely tested prediction in the history of science is the anomalous magnetic moment of the electron. The tiny deviation of the electron's magnetic moment from the value predicted by Dirac's relativistic quantum mechanics arising from quantum field theory corrections. The theoretical prediction of this quantity, computed using the methods of quantum electrodynamics, QED, the quantum field theory of electrons and photons, has been calculated to 11 significant figures. The experimental measurement agrees with the theoretical prediction to the same precision, an agreement of 1 part in 10 billion. No other theory in any field of science makes predictions that precise and has them confirmed to that precision. Chapter 14. The Standard Model. What everything is made of quantum field theory is not a single theory, it is a framework. The specific quantum field theory that describes the known fundamental particles and forces is the standard model of particle physics. Developed over roughly the period from 1961 to 1973 by the combined work of Sheldon Glashow, Steven Weinberg, Abdus Salam, Peter Higgs, Francois Englert, David Gross, Frank Wilczek, David Politzer, and many others, the Standard Model is the most successful physical theory ever constructed in terms of the range of phenomena it describes and the precision of its predictions. The Standard Model consists of 3 quantum field theories corresponding to 3 of the 4 known fundamental forces. There is quantum electrodynamics, QED, which describes the electromagnetic force and its mediation by photons. There is quantum chromodynamics, QCD, which describes the strong nuclear force, the force that holds quarks together in protons and neutrons, and holds protons and neutrons together in atomic nuclei, mediated by gluons. And there is the electroweak theory, which describes both the weak nuclear force, responsible for radioactive beta decay, and the electromagnetic force in a unified framework, mediated by photons, for electromagnetism. W bosons for the charged current weak force, and the Z boson for the neutral current weak force. The matter particles of the Standard Model are 12 fermions, 6 quarks, up, down, charm, strange, top, bottom, and 6 leptons, electron, muon, tau, and 3 associated neutrinos. These 12 particles, plus their antiparticles, are the building blocks of all known matter. Quarks combine in specific combinations to form hadrons. The proton, 2 up quarks and 1 down quark. The neutron, 1 up quark and 2 down quarks. And a wide zoo of unstable particles observed in accelerator experiments. The force carriers of the Standard Model are bosons: the photon, electromagnetic force, 8 gluons, strong force, and the W and Z bosons, weak force. All of these have been directly detected in particle physics experiments. The 12th particle of the Standard Model, the one that completed the picture, is the Higgs boson. The Higgs boson is the quantum of the Higgs field, a scalar field that permeates all of space and interacts with all other particles that have mass. In the Standard Model, particles do not have intrinsic masses. They acquire their masses through their interaction with the Higgs field. Particles that interact more strongly with the Higgs field are heavier. Particles that do not interact with it, like photons, are massless. The process by which particles acquire mass through the Higgs field is called the Higgs mechanism, and it involves a spontaneous symmetry breaking. The Higgs field settles into a non-zero equilibrium value throughout space, and this non-zero value gives rise to the effective masses of the other particles. The Higgs boson was the last particle of the Standard Model to be discovered, found by the ATLAS and CMS experiments at CERN's Large Hadron Collider on July 4, 2012. The search had taken nearly 50 years from Peter Higgs's prediction in 1964. The Higgs boson is unstable. It decays into other particles in about 10 to the power of minus 22 seconds. And detecting it required the most powerful particle accelerator ever built, and the most sophisticated particle detectors in history, built by a global collaboration of thousands of physicists. The discovery was announced by 2 groups working independently, both confirming the signal at a statistical significance of more than 5 sigma, the conventional threshold for discovery in particle physics. François Englert and Peter Higgs received the Nobel Prize in Physics in 2013. The Standard Model has 2 profound limitations that ensure it cannot be the final word in fundamental physics. First, it does not include gravity. General relativity describes gravity with extraordinary success at macroscopic scales, but attempts to construct a quantum field theory of gravity run into mathematical inconsistencies. The naive quantization of gravity, treating the graviton, the hypothetical force carrier of gravity, as a particle in a quantum field theory, produces a theory that is non-renormalizable. The calculations produce infinite answers that cannot be absorbed by redefining physical parameters as they can in QED and QCD. The reconciliation of quantum mechanics and general relativity is the single greatest unresolved problem in fundamental physics. Second, the Standard Model has no explanation for several observed phenomena. Dark matter, whatever it is not one of the Standard Model particles. Dark energy, not described by the Standard Model at all. The matter-antimatter asymmetry of the universe. The Standard Model contains CP violation but not enough to account for the observed asymmetry. And neutrino masses. The original Standard Model predicted massless neutrinos, but experiments since 1998 have confirmed that neutrinos have small but non-zero masses, requiring extensions to the Standard Model. The Standard Model has 19 free parameters, numbers like the masses of the particles, the strengths of the forces, and the mixing angles between different generations that are measured experimentally but not derived from any deeper theory. Complete theory of physics should explain why these parameters have the values they do, not just measure them. The Standard Model cannot do this. Chapter 15: Quantum Gravity. The unfinished business. The two great pillars of modern physics are quantum mechanics, in its most developed form as quantum field theory and the Standard Model, and general relativity, Einstein's theory of gravity. Each is extraordinarily successful in its own domain. General relativity describes the large-scale structure of the universe, the curvature of space-time by mass and energy, the expansion of the universe, the bending of light by gravity, gravitational waves, black holes. Quantum field theory describes the microscopic world of particles and forces with extraordinary precision. But these two theories are fundamentally incompatible. They are built on different mathematical structures, different assumptions about the nature of space, time, and matter, and they make contradictory predictions when applied together. General relativity treats spacetime as a smooth, continuous manifold, a geometric structure that can be curved by the distribution of matter and energy. In general relativity, spacetime is the stage on which physics plays out, and the stage itself is dynamical. It bends and stretches in response to its contents. Quantum field theory, in contrast, takes a flat, fixed spacetime as its background. It describes fields propagating on a static stage. The fields are quantum. They obey the uncertainty principle and can be in superpositions, but the stage is classical. When you try to apply quantum mechanics to gravity, to treat the gravitational field as a quantum field with a quantist excitation, the graviton, the mathematics breaks down. The calculations produce infinitely large quantities that cannot be removed by the renormalization techniques that work for QED and QCD. The theory is non-renormalizable. This is not a technical problem that might be fixed with more sophisticated calculations. It reflects a deep structural incompatibility between the quantum field theory framework and the general relativistic treatment of gravity. The two leading approaches to resolving this incompatibility are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of nature are not point particles, but one-dimensional extended objects, strings that vibrate in different modes. Each vibrational mode corresponds to a different particle. The graviton, the force carrier of gravity, is a specific vibrational mode of the string. String theory automatically produces a consistent quantum theory of gravity because the extended nature of strings smooths out the ultraviolet divergences that destroy the point-particle approach. The price is that string theory requires extra dimensions. The consistent mathematical formulation of superstring theory requires either 10 or 26 dimensions of spacetime. Depending on the version, 6 or 7 of these extra dimensions are assumed to be compactified, curled up at the Planck scale, far too small to be observed. String theory has produced a rich body of mathematical results, including the ADS/CFT correspondence, which has been discussed in previous scripts. But it has not yet produced a unique prediction that distinguishes it from all competitors and that can be tested experimentally. The landscape problem? The fact that string theory has an enormous number, perhaps 10 to the power of 500 or more, of possible vacuum solutions, each corresponding to a different set of physical laws, is the most serious challenge to string theory as a physical theory. With so many possible solutions, it is unclear how to identify the one that corresponds to our universe. Loop quantum gravity, LQG, takes the opposite approach. Rather than starting from quantum field theory and trying to incorporate gravity, LQG starts from general relativity and tries to apply quantum mechanics directly to the geometry of spacetime. In LQG, spacetime itself is quantized. It is not a continuous, smooth manifold, but a discrete network of quantum states. The smallest possible region of space has a specific quantum of area, approximately the Planck area, 10 to the power of minus 70 square meters, and the smallest possible volume is the Planck volume, approximately 10 to the power of minus 105 cubic meters. These are extraordinarily small scales, far smaller than anything any experiment can currently probe. But their existence would have observable consequences in principle, including modifications to the dispersion relation of high-energy photons. High-energy photons would travel at slightly different speeds than low-energy photons. A testable prediction that is currently being constrained by observations of gamma-ray bursts from the Fermi telescope and the LHAASO detector in China. LQG is mathematically consistent in ways that naive quantum gravity is not, but it has not yet reproduced the standard model. It does not, in its current form, describe the matter and force fields of the standard model propagating on the quantized spacetime. Beyond string theory and loop quantum gravity, there are other approaches. Causal set theory, causal dynamical triangulations, asymptotic safety, and others that are being developed with varying levels of mathematical completeness and phenomenological contact. What all approaches to quantum gravity share is the belief that the Planck scale, the scale at which quantum effects in gravity become important, defined by the combination of Planck's constant, the gravitational constant, and the speed of light, at a length of approximately 1.6 times 10 to the power of minus 35 meters, represents a qualitative change in the nature of spacetime. Below the Planck length, the concepts of smooth spacetime geometry and classical position break down completely. The universe at its most fundamental is neither a smooth geometric manifold, as general relativity describes, nor a fixed background spacetime on which quantum fields propagate, as the standard model describes, but something more fundamental still, a structure in which space and time themselves emerge from a more primitive quantum substrate. This is perhaps the deepest question in all of physics. What is the fundamental structure from which space, time, matter, and the laws of physics themselves emerge? We do not know. The mathematics to describe it does not yet exist. The experimental evidence that could discriminate between different proposals is, for the most part, beyond current or foreseeable technology. Conclusion: the deepest map we have. Quantum physics is not one thing. It is a layered structure of successively deeper theories, each more complete and more mathematically demanding than the last, each emerging from the inadequacy of its predecessor in the face of new experimental evidence. At the first layer is non-relativistic quantum mechanics. The wave function, the Schrödinger equation, the Born rule, the uncertainty principle, superposition, entanglement, spin, the Pauli exclusion principle. This layer was assembled in roughly the decade from 1925 to 1935 by a handful of physicists: Heisenberg, Schrödinger, Dirac, Born, Pauli, Jordan, Bohr, working in remarkable intellectual proximity to each other at a moment of concentrated discovery that has few parallels in the history of science. This theory correctly describes atoms, molecules, solid-state physics, chemistry, and the behavior of matter at the energies accessible to most of human experience. It is the most useful scientific theory ever developed, underlying every semiconductor, every laser, every MRI scanner, every solar cell. At the second layer is relativistic quantum field theory, and specifically the Standard Model. The quantization of fields, the Higgs mechanism, the renormalization program, the unification of the electromagnetic and weak forces, quantum chromodynamics. This layer describes all of particle physics and all of the subatomic world, making predictions confirmed to the most extraordinary precision ever achieved in any science. At the third layer, the layer that is not yet complete, is quantum gravity, the reconciliation of quantum mechanics with general relativity, the theory of space-time at the Planck scale, the ultimate account of what space, time, matter, and the laws of physics are made of. This layer remains under construction. What is perhaps most remarkable about this entire edifice is what it says about the nature of the world. At its most fundamental, reality is not a collection of definite objects with definite properties, following deterministic laws and evolving from one definite state to another. At its most fundamental, reality is a quantum state, a superposition of possibilities, each with an amplitude. And the world we experience is in some sense the result of an enormously complex pattern of quantum correlations that decohere into the classical appearances of definite objects and definite properties when examined at the scales of everyday life. The quantum world is not strange because physicists have failed to understand it fully. It is strange because it is genuinely different, not just at extreme scales that humans rarely encounter, but at the root of everything. Every atom in your body is a quantum system. The chemical bonds that hold your molecules together are quantum mechanical. The electrons responsible for your neurons firing are quantum particles, subject to superposition and uncertainty, and the Pauli exclusion principle. The light entering your eyes consists of photons, quanta of the electromagnetic field. The world you experience as solid, definite, and classical is built from a substrate that is none of those things. Feynman's remark that nobody understands quantum mechanics is not a confession of defeat. It is a statement about the depth of the conceptual challenge that quantum mechanics poses. The theory predicts everything correctly. The formalism is complete and unambiguous as a computational tool. What remains open is the interpretation. What picture of reality, if any, corresponds to this formalism? What is the wave function, really? What happens at measurement? Are all branches of the wave function equally real? Does the observer have a special role? These questions are not answered. They are actively being investigated by physicists and philosophers who take the foundations of physics seriously. The history of physics suggests that the resolution will require new concepts as radical as the original quantum revolution, that the picture of reality that eventually emerges from the reconciliation of quantum mechanics with gravity and the solution of the measurement problem will be as different from current quantum mechanics as quantum mechanics is from Newtonian physics. The connection between quantum gravity and the other open problems in fundamental physics is not incidental. The matter-antimatter asymmetry of the universe, the nature of dark matter, the origin of the cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe, the fine-tuning of the parameters of the Standard Model, all of these may ultimately require a theory of quantum gravity for their resolution. The cosmological constant, in particular, is one of the deepest puzzles in physics. The measured value of the energy density of the vacuum is approximately 10 to the power of 123 times smaller than quantum field theory naively predicts. A discrepancy so enormous that it dwarfs any other discrepancy between theory and observation in the history of science. Explaining this discrepancy, why the vacuum energy is so extraordinarily small relative to what the Standard Model would suggest, appears to require either a mechanism that precisely cancels the large quantum contributions, a mechanism for which no satisfying proposal exists, or a fundamental revision of how we understand the relationship between quantum mechanics and space-time. The experimental situation for quantum gravity is both frustrating and, at the edges, beginning to improve. The direct prediction of quantum gravity, the discreteness of space-time at the Planck scale, the Planck length of 10 to the power of minus 35 meters, is 20 orders of magnitude smaller than the scales probed by the Large Hadron Collider. No direct experimental test of quantum gravity at the Planck scale is conceivable with any technology plausibly within reach of human civilization. However, there are indirect observational constraints. The detection of gravitational waves from the laser interferometer. Gravitational Wave Observatory since 2015 has opened a new window on strong field gravity, providing tests of general relativity in the most extreme environments accessible. Deviations from general relativity's predictions, which many quantum gravity theories would produce, have been tightly constrained by these observations. The event horizon. Telescopes' images of black hole shadows provide tests of the geometry of space-time at the event horizon. High-energy cosmic rays and gamma-ray photons from distant sources detected by observatories like El Oya Aso and the Fermi Gamma-Ray Space Telescope constrain Lorentz invariance violation at the level of 1 part in 10 to the power of 19, probing energy scales approaching the Planck scale, albeit indirectly. We are somewhere in the middle of the story, the beginning, the experimental crisis that forced the discovery of the quantum, the decade of feverish development from 1925 to 1935, the refinement into quantum field theory and the Standard Model, is well documented and well understood. The middle, the current state of the theory, with its extraordinary predictive power and its unresolved conceptual foundations, is where we are now. The end, the completed theory of quantum gravity, the resolved measurement problem, the understanding of what the wave function means, is not yet written. What we have is the deepest map of reality that human beings have ever drawn. It is incomplete. It has regions marked "Here be dragons," the Planck scale, the measurement problem, the origin of the laws themselves. But the regions it covers with a precision and a depth that no previous map of reality ever approached. That is remarkable. That is quantum mechanics. One final thought. The physicist Eugene Wigner wrote in 1960 about the unreasonable effectiveness of mathematics in the natural sciences. The mysterious fact that mathematics developed for purely abstract reasons, with no physical application in mind, repeatedly turns out to describe physical reality with extraordinary precision. Quantum mechanics is perhaps the most extreme example of this mystery. The mathematical object of quantum mechanics? Complex valued wave functions in Hilbert space. Linear operators, the Born rule for extracting probabilities, were not derived from any physical intuition about what the world should look like. They were forced on physicists by the data, and they turn out to be correct to a precision that no one in 1925 could have anticipated. Whatever the world is made of at its deepest level, mathematics seems to be the language in which its structure is written. Why this should be so is a question that sits at the boundary between physics and philosophy, and quantum mechanics makes it more acute than any previous scientific development. The deepest map we have is mathematical. The territory, as best we can tell, is too.